Right now, your hand is pressing against something, a chair, a phone, a table, and you have never once actually touched it. The electrons in your skin and the electrons in that surface repel each other so violently that your hand stops short, every time. Physical contact, as you feel it, is an electromagnetic force field pushing back. Zoom in far enough and the solid world dissolves. Atoms, then nuclei, then quarks, and then we hit a wall. A hard, terrifying wall where our best machines go blind and our best equations start breaking apart. We will go through 17 fundamental particles, a universe that is 95% invisible, a particle so rare it decays less than once in 10 billion tries, and the scale where space itself stops making sense. If you enjoy the journey, like and subscribe. It keeps us going. Brace yourselves. We begin. Pick up the closest object near you. Hold it. Feel the weight, the texture, the resistance as you press your fingers against it. You've never touched it. Every single time in your life that you thought you were making contact with something, a force field stopped you. Your skin never reached the surface. The electrons orbiting the atoms in your hand violently repelled the electrons in whatever you were holding. The harder you pressed, the harder the repulsion pushed back. The feeling of touch, the sensation of holding something solid and real, is your nerves reading that electromagnetic resistance. Right now you are hovering over everything you have ever held, and that is just the first layer. Go deeper, and the story gets stranger fast. The atoms making up your hand are themselves almost entirely empty. Picture a football stadium. Now place a single marble on the 50-yard line. That marble is the nucleus. The rest of the stadium, every seat, every hallway, every inch of empty air from the field to the roof, that is the space where electrons move. The solid feeling object in your hand is almost entirely nothing. But the nucleus on the 50-yard line, that is where things get wild. Scientists in the early 20th century assumed the nucleus was the final destination, the end of the line. Ernest Rutherford fired tiny particles at a sheet of gold foil in 1911 and expected them to pass straight through. Most did, but some bounced straight back. He later said it was like firing artillery shells at tissue paper and having them bounce back and hit you. That bounce told him something small and dense was sitting at the centre of the atom. He had just found the nucleus. The world of physics celebrated. The atom had been cracked open, and inside was something concrete, something you could point to. Problem solved. Except the nucleus was not the end. Physicists kept pushing. They built machines that fired particles faster and harder into atomic nuclei. And what came out of those collisions was chaos. Fragments. Pieces of things that had no names yet. By the 1950s and 60s, the list of particles discovered inside the nucleus had grown so long that physicists started calling it the particle zoo. Nobody could make sense of it. There were dozens of particles, then hundreds, all behaving differently, all demanding an explanation. One physicist at the time compared it to discovering a new animal every week. You stop feeling like a scientist and start feeling like a zookeeper with no cages. Every answer was pointing toward a deeper question, and here is the part that should unsettle you. Every layer scientists have ever reached, every time they declared something fundamental and indivisible, turned out to be made of something smaller. The molecule held the atom held the nucleus held protons and neutrons, and protons and neutrons. They were holding something else entirely, something that to this day we have never been able to pull apart and look at directly. Your body is built from these things. Your chair, your phone, the air in your lungs, all of it assembled from pieces we cannot fully see or separate. Every solid thing you have ever trusted with your weight is, at its deepest level, a system of rules and forces we only partially understand. And the closer we look, the more the rules start to bend. The next layer down is where the real mystery begins. Scientists gave these inner pieces a name. They called them quarks. And the moment they did, physics changed forever. Scientists knew atoms existed long before they could see them. For most of history, the atom was a philosophical idea. Ancient thinkers in Greece proposed that matter, if you kept cutting it smaller and smaller, would eventually reach a piece so tiny it could not be divided further. They called it atomos, which means uncuttable. For over 2,000 years, nobody could prove it. The atom sat in the realm of guesswork. Then chemistry changed everything. In the early 1800s, a scientist named John Dalton studied how elements combined with each other. He noticed that elements always combined in fixed whole number ratios. Hydrogen and oxygen always made water in the same proportions every single time. That level of consistency pointed to something real, something countable. Dalton proposed that each element was made of its own unique type of tiny particle, and that these particles were the building blocks of all matter. The atom had moved from philosophy to science. But for nearly a century more, nobody knew what was inside one. The assumption was simple. Atoms were solid. Dense little spheres, uniform all the way through. Some physicists pictured them like tiny billiard balls. Others imagined them as positively charged spheres with negative charges embedded inside like raisins in a pudding. Neat, organised, understandable. Then Rutherford took a piece of gold foil thinner than anything you could see with your naked eye and started shooting at it. He was firing particles called alpha particles, the same type that stream out of certain radioactive materials. Most of them pass straight through the foil, as if it were not there. That was expected, but one in every 8,000 bounced back, straight back, almost directly back toward the machine that fired them. Rutherford spent months trying to explain that. He eventually concluded the only possible answer was that nearly all the mass of an atom is packed into a tiny, dense core sitting at the centre. The rest of the atom is open space, vast, empty, mostly nothing. That core is the nucleus, and it is almost impossibly small compared to the atom surrounding it. If you scaled an atom up to the size of a professional baseball stadium, the nucleus would be smaller than a pea sitting at the centre of the field. Everything else, the towering stands, the concourse, the parking lot outside, all of that represents the empty space where electrons travel. The atom is overwhelmingly hollow. The electron cloud around the nucleus is what gives matter the appearance of being solid. Electrons move so fast and create such a dense electromagnetic barrier that nothing from the outside can easily get through. That barrier is what your fingers are pressing against when you hold something. Pure electromagnetic resistance. And the nucleus at the centre of all of this? Tiny as it is, it turns out to be packed with structure. Scientists discovered that the nucleus contains two kinds of particles. Protons, which carry a positive electric charge, and neutrons, which carry no charge at all. Both are tightly bound together by a force so powerful it overcomes the natural repulsion between all those positive protons trying to push each other away. That force has a name, and understanding it would take decades of work, enormous machines, and the realization that protons and neutrons were, themselves, made of something even smaller. The nucleus looked like the final answer. It was not, and what physicists found hiding inside it would rewrite every textbook on Earth. By the 1950s, physicists were drowning. They had started with atoms, found nuclei, found protons and neutrons inside those nuclei, and assumed the work was nearly done. Matter had been cracked open, and the pieces were on the table. Clean, manageable. Then the accelerators turned on. Particle accelerators are machines that fire subatomic particles at each other at speeds approaching the speed of light. When those particles collide, the energy of the impact sprays out in all directions, producing new particles that detectors record and measure. Think of it like smashing two watches together at full speed and studying every gear, spring, and fragment that flies out. Except the watches are protons, and the fragments are things nobody has ever seen before. In the 1940s and 50s, accelerators around the world started producing results that confused everyone. Every time physicists smashed particles together at a new energy level, something new came out. A pion, a kaon, a lambda particle, then a sigma, a xi, a delta, then particles with strange behaviour that did not match any prediction. The list kept growing. By the early 1960s, physicists had discovered over 100 distinct particles. Some lasted for billionths of a second before decaying into something else. Some barely existed at all. There was no clear pattern, no organizing principle, no reason why any of them existed. One physicist, Enrico Fermi, told a young student that if he had known there would be this many particles to memorize, he would have gone into botany instead. The particle zoo was a mess, and a mess in physics means something is missing. Murray Gell-Mann noticed something. He was a young physicist at the California Institute of Technology, and he had a talent for finding patterns where others saw noise. Looking at the growing list of particles and their properties, he noticed that certain groups shared mathematical relationships. When he arranged them in a specific geometric pattern, something appeared: gaps, empty slots where particles should exist but had not yet been discovered. He predicted an entirely new particle based on those gaps. He called it the Omega Minus. Experimenters went looking for it. They found it in 1964, exactly where Gell-Mann said it would be. That was the moment physicists knew the zoo had rules. Gell-Mann's organizing system hinted that all these particles were combinations of something smaller. He proposed that protons, neutrons, pions, kaons, and every other particle in the zoo were all built from a set of smaller, truly fundamental pieces. He called them quarks, borrowing the word from a line of poetry by James Joyce. The name stuck. A physicist named George Zweig came up with the same idea independently at almost the same time. He called his version ACEs. History remembers quarks. At first, most physicists dismissed the idea. The math worked on paper, but nobody expected quarks to be real physical objects. They seemed more like a bookkeeping trick, a useful fiction for organizing equations. A particle called a quark that always came in groups and could never be pulled out alone seemed almost too convenient to be real. But the data kept pointing in one direction, and a machine on the other side of the country was about to fire a beam of electrons at a proton, and for the first time catch something hard and small bouncing back from inside it. Something was in there, and it was about to change everything. In 1968, a team at the Stanford Linear Accelerator Center did something that should have been impossible. They looked inside a proton. The Stanford Accelerator was a straight tunnel 2 miles long, buried underground in California. It fired electrons at close to the speed of light, not at each other, at protons. The goal was to see what happened when something that small and fast hit a proton dead on. The expectation was that the electrons would scatter gently, spreading out in soft, wide angles the way a wave spreads when it hits a smooth wall. A proton, most physicists assumed, was a smooth, uniform blob of charge, soft inside, no hard structure. What the detectors recorded was completely different. Some electrons were bouncing back at steep, sharp angles, hard deflections, like firing a beam of marbles at a bag of sand and watching some of them bounce straight back. That does not happen unless there is something hard and dense sitting inside the bag. Something was in there. Multiple somethings. Small, point-like, carrying electric charge. The electrons were hitting them and bouncing off hard. The team called these internal structures partons at first, meaning parts of the proton. They were measuring the charge and behavior of these inner pieces without being able to pull them out. It was like feeling the shape of a stone through a wet paper bag. You could not see it directly, but the way it pushed back told you exactly what was there. This was the first real experimental evidence that quarks were physical objects, not just mathematical tools. The results sent shockwaves through physics. Gell-Mann had predicted quarks using pure pattern recognition and mathematics. Now there was physical evidence. Protons were made of smaller things. Those smaller things were real. And the zoo of particles that had confused an entire generation of physicists suddenly started making sense as combinations and rearrangements of these fundamental pieces. But the Stanford results also revealed something unsettling. The quarks inside the proton were moving. Rapidly. They were not sitting still like marbles in a jar. They were bouncing around at significant fractions of the speed of light, exchanging energy, interacting constantly. And the force holding them together was unlike anything physicists had seen before. When you try to pull two magnets apart, the force between them weakens as the distance grows. Almost every force in nature works this way. The farther apart two things get, the less they pull on each other. The force between quarks does the opposite. Pull two quarks apart and the force holding them together gets stronger. The farther you try to separate them, the harder the force pulls back. It behaves like a rubber band stretched to its limit, except this rubber band never breaks. Instead, if you pump enough energy into pulling them apart, that energy converts into brand new quarks. You end up with more quarks, still bound together, still refusing to separate. A single free quark has never been detected. Not once, in any experiment ever conducted. This bizarre rule would later be named quark confinement, and it means that the fundamental building blocks of all visible matter are permanently locked away, hidden inside larger particles, impossible to isolate and study directly. That was a serious problem, and the deeper physicists dug, the stranger it got. By the 1970s, physics needed a framework. The particle zoo had been tamed. Quarks were real. The forces holding matter together had been studied, measured, and described with equations of striking accuracy. But all of this knowledge was scattered across separate theories, separate teams, separate frameworks that did not speak to each other. Physicists needed one rulebook, one coherent description of everything known about matter and its interactions. What emerged from those years of work is called the Standard Model. Think of it as the periodic table of reality. The periodic table organizes all chemical elements by their properties and tells you how they combine. The Standard Model does the same thing for the most fundamental pieces of existence. It lists every known particle, describes every known force between them, and explains how matter behaves at the smallest scale we can access. The model identifies 17 fundamental particles, 6 quarks, 6 leptons, 4 force-carrying particles, and the Higgs boson. Each one has specific properties: mass, charge, spin. Each one plays a defined role. Together they account for every atom, every molecule, every material, every chemical reaction, every light wave, every electric current that has ever existed. The Standard Model is the most precisely tested scientific theory ever written. At its best, it predicts experimental outcomes to an accuracy of 1 part in a trillion. Imagine measuring the distance from New York to Los Angeles, which is roughly 2,800 miles, and being accurate to within a fraction of an inch. That is the level of precision physicists are talking about when they describe how well the Standard Model matches reality. And yet, gravity is completely absent. Every other force in nature, the electromagnetic force that holds electrons in atoms, the strong nuclear force that holds quarks in protons, the weak nuclear force that governs radioactive decay, they all fit inside the Standard Model with descriptions, carrier particles, and clean mathematical rules. Gravity has none of that. Physicists have tried for decades to fit gravity into the Standard Model and failed every time. The mathematics breaks down. The equations produce answers like infinity, which in physics means the model is wrong, not that infinity is the answer. Gravity governs everything at large scales: planets, stars, galaxies, the structure of the entire cosmos. The Standard Model governs everything at small scales, and the two descriptions are fundamentally incompatible. Running them simultaneously produces nonsense. That incompatibility is one of the deepest unsolved problems in all of science, and gravity is just the beginning of what the Standard Model gets wrong. The model predicts that neutrinos, tiny ghost-like particles that pass through ordinary matter by the trillions every second, should have zero mass. Measurements have confirmed they have mass. Small, but real. The rulebook is wrong about one of its own particles. The model also has nothing to say about why matter vastly outnumbers antimatter in the observable universe. According to the physics of the Big Bang, equal amounts of both should have been created. Somehow, matter won. The Standard Model offers no explanation. And then there is the biggest gap of all. Everything the Standard Model describes, every particle, every force, every atom in every star, accounts for only 5% of the total content of the universe. The other 95% is something else entirely, and nobody knows what. The universe should not look the way it does. Galaxies spin. Stars orbit the centre of their galaxy in enormous sweeping arcs. And when astronomers in the 20th century measured how fast those stars were moving, they found something that broke the math. Stars on the outer edges of galaxies were moving too fast. Way too fast. In a galaxy held together only by the gravity of its visible stars and gas, the outer stars should be moving slower, the same way the outer planets in our solar system move slower than the inner ones. Mercury races around the Sun, Neptune crawls. The farther you are from the centre of the gravitational pull, the slower you move. But the outer stars in galaxy after galaxy were orbiting at nearly the same speed as the inner ones. Some were moving even faster. By the rules of gravity as we understand them, they should have been flung into deep space billions of years ago. Something was holding them, something with mass, something that created gravitational pull, something invisible. Astronomer Vera Rubin spent years documenting this problem across dozens of galaxies in the 1970s. The pattern was identical everywhere she looked. Outer stars moving too fast. Gravity from visible matter too weak to explain it. Whatever was holding those galaxies together was outweighing all the visible stars and gas by a factor of roughly 5 to 1. Scientists gave it a name: dark matter. Not because it is dark in colour, but because it emits no light, reflects no light, and absorbs no light. It is gravitationally real, but optically invisible. Every telescope ever built cannot see it directly. Its presence is inferred purely from the way it bends the path of light and tugs on everything around it, and dark matter is only part of what is missing. In the late 1990s, 2 independent teams set out to measure how fast the universe was expanding after the Big Bang. Everyone assumed the expansion was slowing down. Gravity pulls things together. A universe full of matter should be decelerating over time, the same way a ball thrown upward slows down before it falls. Both teams measured the opposite. The expansion of the universe is speeding up. It is accelerating outward. Something is pushing the fabric of space itself apart, overpowering gravity on cosmic scales. Something with energy spread evenly across all of space, in every direction, at every point, all at once. They called it dark energy, and nobody has any idea what it is. Dark matter accounts for roughly 27% of the universe. Dark energy accounts for roughly 68%. Everything you have ever seen, touched, learned about, or built technology to detect, every star, every planet, every atom in every living thing, adds up to about 5% of what actually exists. The Standard Model, the most precisely tested theory in scientific history, describes that 5% and nothing more. The other 95% stands completely outside it. No particle in the Standard Model matches dark matter. No equation in the Standard Model explains dark energy. These are deep structural gaps in human knowledge, and they have not narrowed in 50 years of searching. Physicists have proposed candidates for dark matter: weakly interacting massive particles, sterile neutrinos, primordial black holes. Detectors have been buried deep underground, shielded from cosmic radiation, waiting for a dark matter particle to bump into something detectable. Silence. Decades of searching. Enormous machines. The most sensitive instruments humans have ever built. And the thing that makes up more than a quarter of the universe has never once shown up in a detector. Whatever the next layer of reality is made of, it is not in the Standard Model. July 4th, 2012 was a good day for physics. 2 separate teams working at the Large Hadron Collider at the European Physics Laboratory known as CERN announced they had found it, the last missing piece of the Standard Model. A particle physicists had been hunting for nearly 50 years, the particle that explains why other particles have mass at all, the Higgs boson. The announcement made global headlines. Scientists in the auditorium at CERN were visibly emotional. Some cried. The physicist who first proposed the Higgs mechanism back in 1964 was there in the room to see it confirmed. He also cried. The Standard Model was complete. For a moment it felt like a finish line had been crossed. The rulebook for all of matter, all the particles and forces had been written, tested, and now fully confirmed. Every piece predicted by the theory had been found. The search was over, except it was not. Completing the Standard Model did not close the mystery of the universe. It clarified exactly how large that mystery is. The Higgs boson confirmed that a field called the Higgs field permeates all of space. When particles move through this field, they interact with it, and that interaction is what gives them mass. The Higgs particle is the ripple you see in that field when you disturb it, the same way a wave is the ripple you see when you disturb water. But here is what the Higgs discovery did not answer. Neutrinos have mass. The Standard Model says they should not. The Higgs mechanism, even now fully confirmed, does not cleanly explain where neutrino mass comes from. The model is internally inconsistent on this point, and physicists have known it for years. The Higgs boson also has a mass that troubles theorists. Based on the other properties of the Standard Model, the Higgs should have been pulled by quantum effects to an enormously high mass, far beyond what was measured. Instead, it came in surprisingly lightweight. Keeping it at that low mass requires such a precise cancellation of quantum effects that many physicists find it implausible. Some call this the hierarchy problem. Others call it fine-tuning. Both names point to the same concern. The model works, but it feels rigged. And then there is the larger picture. The Large Hadron Collider is the most powerful particle accelerator ever built. Its tunnel is 17 miles around, buried under the border between France and Switzerland. It has run millions of collisions at energies no machine before it could reach. And the discovery it is most famous for, the Higgs boson, was the last predicted particle of the Standard Model. Since then, the collider has found nothing new. Every collision, every data set, every analysis has come back consistent with the Standard Model and nothing beyond it. Physicists had hoped to find hints of deeper physics, new particles, deviations from predictions, something pointing toward the next layer of reality. The data has been stubbornly clean. That silence is not reassuring. It means either the Standard Model really does describe everything at the energy scales humans can currently reach, or the next layer of reality is hiding at scales so small that even the most powerful machine ever built cannot touch it. Both possibilities lead to the same place, a wall, a boundary, where current tools stop working, and something on the other side that we cannot yet see. Every force you have ever encountered works the same way. Pull two magnets apart and they lose their grip on each other. Step farther from a fire and the heat fades. Gravity weakens with distance. Every force in everyday experience follows a simple rule. The farther apart two things are, the weaker the force between them. The strong nuclear force does the exact opposite. The strong nuclear force is what binds quarks together inside protons and neutrons. It is carried by particles called gluons, and it is extraordinarily powerful at close range. It has to be. Protons are made of multiple positively charged quarks crammed together, and positive charges repel each other fiercely. Only something stronger than an electromagnetic repulsion could hold them in place. The strong force handles that with room to spare. At the distances inside a proton, it is roughly 100 times stronger than the electromagnetic force. But here is what makes it unlike any other force in nature. As you try to pull two quarks apart, the strong force between them does not weaken. It stays constant. Then it begins to grow. The farther apart the quarks get, the harder the force pulls them back together. Physicists sometimes describe it like a rubber band stretched between the quarks. The more you stretch it, the more tension builds. Except this rubber band never snaps. If you keep pumping energy into the system trying to separate two quarks, something else happens entirely. At a certain point, the energy you have added to the system is enough to create brand new particles. The field between the straining quarks rips apart and produces a new quark-antiquark pair from that energy alone. So instead of one isolated quark, you now have two new pairs of quarks, each pair bound together. You started with two quarks trying to separate. You ended up with four quarks, still confined. A single free quark has never been detected in any experiment in the history of physics. This rule is called confinement, and it creates a serious problem for anyone trying to study quark structure. To understand what quarks are made of, if they are made of anything at all, you need to probe them directly. You need to separate them, isolate them, examine them individually, and the laws of physics prevent you from doing that. It is like being told that a box contains something fascinating, handed a pair of gloves too thick to feel what is inside, and informed that the box will seal tighter the harder you grip it. The indirect evidence for quark structure still exists. The way quarks scatter particles, the way they absorb and emit energy, the way they respond to extremely high energy probes, all of it suggests they behave like point-like objects at the scales physicists can currently reach. No internal structure has been detected yet, but no internal structure detected yet is very different from no internal structure exists. Every particle physicists ever called fundamental turned out to contain something smaller. The atom contained the nucleus. The nucleus contained protons and neutrons. Protons and neutrons contained quarks. The pattern has repeated itself at every layer. Nothing in the laws of physics says quarks have to be the end, and some physicists refuse to believe they are. They have built an entire theoretical framework around the possibility that quarks contain something smaller, something that, if proven real, would collapse and rebuild everything we understand about matter. They call these hypothetical inner pieces preons, and the theory around them is one of the most controversial ideas in modern physics. Stop thinking about particles for a moment. Every picture you have ever seen of an atom shows tiny spheres orbiting a central cluster of spheres. Electrons as small balls, quarks as smaller balls inside, protons as neat round objects sitting in a nucleus. Physics textbooks and science posters worldwide have drilled that image into your head since childhood. That picture is wrong. The actual deepest layer of known reality is not made of tiny spheres. It is made of fields. A field, in physics, is not a meadow. It is a mathematical object that has a value at every single point in space. Temperature is a field. Every location in a room has a temperature, and that temperature can be higher or lower than the point next to it. An electromagnetic field is similar. It has a strength and direction at every point in space simultaneously. Quantum fields are the same concept. Pushed to the deepest level of reality, the universe is filled with overlapping quantum fields, one for each type of fundamental particle. There is an electron field, a quark field, a photon field, a Higgs field. These fields exist everywhere, in every cubic inch of space, from the center of stars to the emptiest regions between galaxies. Particles are ripples in these fields. When an electron appears, it is because the electron field at that location has been disturbed. The electron is the disturbance, the way a water wave is not a separate thing from the water, but a pattern moving through it. When the disturbance settles, the electron is gone. The field is still there, waiting. This means that what we call empty space is, at the quantum level, seething with activity. Every quantum field that exists has what physicists call a ground state, a minimum energy level even when no particles are present. Quantum mechanics prevents the field from sitting completely still. There is always a tiny, unavoidable fluctuation. These fluctuations constantly produced pairs of virtual particles, one particle and one antiparticle, that snap into existence and annihilate each other so fast that no detector can catch them in the act. Physicists call this the quantum vacuum, and the quantum vacuum is anything but empty. Picture a pot of water just below the boiling point. On the surface it looks calm, but underneath, microscopic bubbles are forming, collapsing, forming again constantly. The quantum vacuum behaves like that, but at a scale so small it makes a bubble look like a planet. These vacuum fluctuations are real. They have measurable effects. Two metal plates placed extremely close together in a vacuum will be pushed toward each other by the fluctuating fields in the space between them. That push has been measured in laboratories. It is called the Casimir effect, and it is direct proof that empty space is physically active. This completely changes what matter is. You're not a collection of tiny balls. You're a set of patterns in overlapping fields. The quarks inside your protons are disturbances in the quark field. The electrons around your atoms are disturbances in the electron field. The light hitting your eyes right now is a ripple in the photon field. None of them are solid objects. None of them have firm edges. If quantum fields are the true foundation of matter, then the next question is obvious. Are the fields themselves the final layer? Or are the fields made of something? Nobody knows, and the machines that might answer it do not exist yet. 6 types of quarks exist in the Standard Model. Physicists call them up, down, charm, strange, top, and bottom. The names have no deeper meaning. They're just labels, like calling 6 different breeds of dog by colour instead of name. What matters is what they weigh and how they behave. The lightest quarks, the up and down quarks, are the ones that build protons and neutrons. They are extraordinarily light, so light that most of the mass of a proton does not actually come from them at all. The 3 quarks inside a proton together account for only about 1% of the proton's total mass. The rest comes from the binding energy of the strong force holding them together. Pure energy converted into effective mass by the most famous equation in physics. That is already strange, but compare those tiny quarks to what sits at the other end of the list, the top quark. The top quark is a fundamental particle. It has no detected internal structure. It is, as far as physicists can tell, a point-like object with no size, and it weighs about as much as an entire atom of gold. One particle, the same mass as 175 billion electron volts. An atom of gold contains 79 protons, 79 electrons, and 118 neutrons. Each of those contains multiple quarks, and the top quark, a single fundamental object, matches that entire atomic mass. Nobody knows why. The Standard Model does not explain the masses of the quarks. It allows for those masses, but it does not derive them from any deeper principle. The mass of the top quark compared to the mass of the up quark differs by a factor of roughly 80,000. Why the same type of object would have such radically different masses depending on which flavour it is has no accepted answer. This mass pattern is one of the deepest puzzles in particle physics. It hints that there may be structure, a reason, a deeper organising principle that determines these masses and that the Standard Model does not capture. The top quark also has one of the shortest lifetimes of any known particle. It decays almost instantly after being created, so fast that it falls apart before the strong force can bind it into a larger particle. It exists for roughly 500 times 10 to the power of negative 27 seconds. That number is incomprehensible in everyday terms. A camera that could photograph the top quark would need to take more frames per second than the number of atoms in the observable universe. Because of this, the top quark has never been studied inside a bound system. It always decays alone. That isolation actually makes it useful. Its decay products carry clean information about its mass and properties without the complications that confinement adds to lighter quarks. Physicists study the top quark like a medical examiner studying a body. The subject is gone by the time the examination starts, but the evidence left behind still tells a full story. And what that story suggests is troubling. The top quark's extreme mass compared to its fellow quarks implies that the Standard Model's list of particles may be a surface pattern sitting on top of something deeper, something that sets the rules about mass, something not yet discovered, that something may leave traces in places you would not expect, places where particles decay in unusual ways, following paths that should be rare, and sometimes acting just slightly off from what the Standard Model predicts. Those tiny deviations are where the next layer of physics might be hiding. Every time physics found a supposedly final particle, that particle turned out to have components. Atoms held nuclei. Nuclei held protons and neutrons. Protons and neutrons held quarks. Each time the story was the same. A generation of physicists declares something fundamental, and the next generation finds it is made of smaller parts. Some physicists decided that waiting for history to repeat itself was too slow. They started working backward from the evidence. If quarks are made of something smaller, what properties would those smaller things need to have to produce the quarks we observe? The result of that thinking is the preon hypothesis. Preons are hypothetical particles, proposed building blocks that would sit one level below quarks and leptons in the hierarchy of matter. The word comes from pre-quark. The core idea is that the 6 different quark flavors and the 6 different leptons are not truly fundamental. They are different combinations or arrangements of a smaller set of truly elementary objects. The strongest argument for preons is the pattern problem. The standard model lists 12 matter particles, 6 quarks, and 6 leptons. They arrange into 3 groups called generations, where each generation is essentially a heavier copy of the previous one. The electron, the muon, and the tau particle behave identically in terms of their interactions, but differ wildly in mass. The same pattern repeats for neutrinos and for quarks. When physicists see a pattern like that in nature, it almost always means an underlying structure is organizing things. The periodic table showed the same kind of repetition across elements, and that repetition eventually revealed the electron configuration inside atoms. 3 generations of matter particles, each a heavier echo of the last, strongly suggests something is generating that pattern from below. Preons would be that something. If each quark is a specific combination of 2 or 3 preons, then the 6 quark flavors become 6 different arrangements of the same underlying components, the same way 6 different words can be spelled from the same small set of letters. The repetition is explained. The pattern has a cause. But preons carry a serious problem. To fit inside a quark, a preon would need to be at least 1,000 times smaller than the quark itself. And to confine something that small inside something that small, the energy binding them together would need to be enormous. Quantum mechanics sets a hard rule. The smaller the space a particle is confined in, the higher its energy must be. This is called the uncertainty principle. If preons exist and are confined inside quarks at that scale, they should carry enormous energy. That energy should show up as enormous mass. But quarks, especially the lightest ones, are not very massive at all. This is called the preon mass problem, and no proposed preon model has fully solved it. Some physicists have suggested the binding energy of preons cancels itself out through supersymmetry or other mechanisms, leaving the quarks with their observed low masses. The math works in some models, but none of those models has made a clear, testable prediction that any existing experiment could confirm. To test the preon hypothesis directly, you would need to smash quarks together hard enough to break them apart, and the energy required to do that is so far beyond current technology that the machines needed do not exist and could not be built with any engineering approach available today. The preon hypothesis is a serious scientific idea held by serious physicists, and right now it sits exactly where quarks sat in 1963, mathematically motivated, physically plausible, and completely unconfirmed. Something much stranger might confirm it, or rule it out. But the answer requires a machine that does not yet exist. Physics has a problem that has nothing to do with equations. It has to do with size. To study the smallest structures in nature, physicists use particle accelerators. The basic principle is simple. Accelerate particles to enormous speeds, smash them together, and analyze what comes out. The higher the energy of the collision, the smaller the structures you can probe. Energy and resolution are directly linked. To study an atom, you need energies in the range of electron volts. To study a nucleus, you need millions of electron volts. To study a proton's internal structure, you need billions. The Large Hadron Collider reaches trillions of electron volts, which is why it can study quarks at the scales it does. To study what is inside a quark, if anything, you would need far more. The energy required to probe structure at the scale where preons or any subquark physics might live is roughly 10 million trillion electron volts. The Large Hadron Collider currently reaches about 13 trillion. The gap between what we have and what we need is a factor of roughly 1 million. Building a machine powerful enough would require an accelerator ring not 17 miles around, like the Large Hadron Collider, but millions of miles in circumference. Larger than the orbit of the Moon. That is the energy wall, and it gets worse. Some theoretical physicists believe that beyond a certain energy threshold, the act of probing matter creates a new problem entirely. At the Planck energy scale, The energy of collisions would be so extreme that the particles being smashed together would form a black hole at the point of impact. The collision would collapse into a singularity before any information about inner structure could escape. If that is true, it is an absolute limit, a physical ceiling on human knowledge, built into the structure of the universe. You cannot see past a certain scale, because the act of looking destroys the thing you are trying to see. This is not a confirmed limit. It is a theoretical concern, and physicists debate it seriously. But the possibility that reality contains a hard epistemic wall, a depth below which no observation is ever possible by anyone anywhere in the universe, is one of the most unsettling ideas in modern science. The proposed response to the energy wall is not to give up. It is to be clever. The next generation of accelerators being designed today aims to reach energies roughly 10 times higher than the current record. The proposed future circular collider would be a tunnel roughly 60 miles in circumference, nearly 4 times larger than its predecessor. Planning and early construction discussions are underway, but the machine is not expected to begin high-energy physics experiments until around 2070. That is roughly 50 years away. In the meantime, physicists are developing a completely different strategy, a way to look deeper without building bigger, a method of detecting hidden physics at scales beyond direct reach, using rare and delicate measurements as a kind of listening device. The idea is that particles deep below the observable scale would still leave tiny fingerprints on the particles we can detect. They would nudge decay rates slightly off from predictions. They would shift masses by fractions of a percent. They would show up as small but persistent errors in the equations. All you need to find them is a measurement precise enough to notice, and in 2022 something showed up that the standard model could not explain. In 2022, a team of physicists at the Collider Detector Facility at Fermilab in Illinois announced a result that rattled the physics community. They had spent years making the most precise measurement ever taken of the W boson's mass. The W boson is one of the force-carrying particles in the standard model. It is responsible for a type of nuclear decay called the weak interaction, the same process that converts a neutron into a proton inside certain radioactive atoms. The W boson is a well-studied particle. The standard model predicts its mass with high precision, based on the interactions it must have with other particles. The Fermilab team measured it more precisely than any group before them. They analysed roughly 4 million W bosons produced by their accelerator. They applied corrections for every known source of measurement error. They checked the result repeatedly over years of work before publishing. The number came in wrong. The W boson was heavier than the standard model predicts, not by much, roughly 0.1%. In everyday life, that sounds trivially small. But in particle physics, a 0.1% discrepancy at that level of precision is not a rounding error, it is a signal. The measurement disagreed with the standard model's prediction by a margin that physicists express in units called standard deviations. The Fermilab result sat at 7 standard deviations from expectation. In physics, 5 standard deviations is the conventional threshold for calling something a discovery. 7 means the odds of the discrepancy being a statistical accident are roughly 1 in a trillion. Something about the standard model's description of the W boson appears to be incomplete. The immediate response from the physics community was cautious. A result this significant demands verification. Other experiments using other instruments have measured the W boson mass, and some of those earlier results align more closely with the standard model prediction. The measurements are in tension with each other, which means the experimental picture is not yet fully resolved. But the Fermilab measurement was careful, meticulous. It represents the largest dataset ever used for a W boson mass measurement, analysed with the most refined methods available. Dismissing it entirely would require explaining what went wrong in a decade of meticulous work by one of the most experienced teams in the field. If the result holds, it means something beyond the standard model is interacting with the W boson and shifting its mass. A new force, a new particle, a new field not yet accounted for in the current rulebook. Even a 0.1% error in a fundamental mass prediction is enough to unravel the entire theoretical framework built around it. The Standard Model is a tightly interlocked system. Change one value and cascading inconsistencies ripple through the rest of the theory. Physicists around the world began running new analyses. Several theoretical papers within months of the announcement proposed specific models for what might be causing the shift. Some invoked supersymmetry, a theoretical extension of the Standard Model that predicts heavier partner particles for every known one. Others proposed new gauge bosons or additional Higgs-like fields. All of them pointed in the same direction. Something is out there beyond the Standard Model, and the W boson was not the only crack in the wall. Deep inside the Large Hadron Collider, billions of collisions happen every second. Most of them produce ordinary results. Particles smash together, spray apart, decay into smaller pieces, and leave tracks in detectors that physicists analyze for months or years. The overwhelming majority of those events match the Standard Model exactly, but a small number of them do something unexpected. Over the past decade, experiments at the Large Hadron Collider have tracked the decay of particles called beauty mesons, sometimes called B mesons. A beauty meson is a particle that contains one beauty quark, also called a bottom quark, bound together with another quark. Because the beauty quark is relatively heavy, beauty mesons are unstable and decay quickly into lighter particles. The Standard Model predicts with high precision how often beauty mesons should decay into specific sets of lighter particles. Some decay modes produce electrons, others produce muons, which are heavier copies of electrons with identical charge but about 200 times the mass. According to the Standard Model, electrons and muons are the same in every way that matters for these decays. The theory predicts they should be produced in equal numbers. They are not being produced in equal numbers. Multiple measurements across the Large Hadron Collider beauty experiment and the Bell detector in Japan have shown that decays producing muons are happening less often than decays producing electrons. The difference is small but consistent. Across many years of data and multiple independent measurements, the same pattern shows up. This matters because it should not happen. If electrons and muons are treated identically by the forces involved in these decays, they should appear at the same rate. Any deviation from equal production means some force or particle is treating them differently. Something is distinguishing between electrons and muons in a way the Standard Model does not account for. Physicists call this lepton universality violation, and it is considered one of the most significant anomalies in current experimental data. The statistical confidence of the individual measurements has shifted as data has grown. Some earlier measurements suggested very high significance. More recent combined analyses have moved the confidence level to roughly 3 to 4 standard deviations. That sits below the 5 sigma threshold for a formal discovery, but it sits firmly above the level that careful physicists dismiss. The most popular theoretical explanation for this anomaly involves a hypothetical particle called a leptoquark. A leptoquark would be a new kind of particle that interacts with both quarks and leptons simultaneously. In the Standard Model, quarks and leptons belong to completely separate families that interact only indirectly. A leptoquark would bridge that gap, coupling directly to both families and creating interactions that could shift the decay rates of beauty mesons in exactly the pattern being observed. Leptoquarks have never been detected. They appear in several theoretical extensions of the Standard Model, including some grand unified theories that attempt to merge the strong electromagnetic and weak forces into a single framework. If a leptoquark were confirmed, it would be the first direct evidence of a new fundamental force connecting two particle families that have always been treated as separate. And it would mean that the Standard Model, the most precisely tested framework in science, is leaving out an entire category of interaction. The search for that interaction is now running in parallel with the search for confirmation of the W boson anomaly. Two cracks in the same foundation, both small, both persistent, both pointing towards something waiting just out of reach, and both about to be joined by a third. There is a smarter way to look for something you cannot reach. You do not need to touch it. You just need to listen for the noise it makes when it affects things you can reach. This is the strategy physicists have developed for exploring the Zeptuniverse. the scale 1 quintillion times smaller than a meter, where the standard model may stop working and something new may begin. A theoretical physicist named Andrei Burras has spent years developing this approach. His core argument is simple. New particles at extremely small scales still influence the behavior of particles at larger scales. They change decay rates, they shift probabilities, they leave tiny, predictable fingerprints on processes that can be measured in a lab. The fingerprint Burras and his colleagues focus on is rare decay. Some particle decays are extraordinarily rare. The standard model predicts that certain particles will decay into specific combinations of products only once in billions or trillions of attempts. These rare decays are exquisitely sensitive to interference. If a new particle or force exists at a scale far below what accelerators can directly probe, it will alter the rate of these rare decays by a detectable amount, even if the particle itself is far too small to be seen directly. The particle Burras finds most useful for this purpose is the kaon. A kaon is a particle containing one strange quark, bound with one up or down quark. It is heavier than a pion but lighter than most other mesons, and in one very specific decay mode, a charged kaon decays into a charged pion plus a matter-antimatter particle pair. The kaon behaves with extraordinary rarity. The standard model predicts this decay happens fewer than one time in 10 billion attempts. 1 in 10 billion. If you watched a single kaon for its entire lifetime, the odds of seeing this decay are vanishingly small. That rarity is the entire point. A decay that happens only once in 10 billion tries is so sensitive to any interference from hidden physics that even a tiny new force would push the rate noticeably up or down. Measuring the exact rate of this decay and comparing it to the standard model's prediction is like listening to a silent room for the faintest possible sound. Any deviation is immediately visible. In September of 2024, the experiment named NA62 at the European Physics Laboratory ran long enough and with sufficient sensitivity to record that ultra-rare kaon decay. The result was historic. The first time any experiment had measured this decay with enough precision to meaningfully compare against theoretical predictions. The result was consistent with the standard model, but the measurement uncertainty is still large enough that significant deviations from new physics could be hiding inside it. The next round of measurements will tighten that window dramatically. This is indirect observation as a scientific tool. Physicists cannot build a machine that directly touches the Zeptuniverse scale. The energy wall prevents that, so they build a machine sensitive enough to hear whispers from it. Each rare decay measured, each precision result refined, narrows the range of possibilities for what lies below. The expected next generation of colliders, including upgrades to existing experiments and eventually the future circular collider, will push these measurements to levels of precision where deviations from the standard model at the part per million level become detectable. Every measurement that matches the standard model exactly is also useful. It rules out entire classes of theories about what lies below. The search is advancing even when the answer looks quiet. But the scale being probed by all of these experiments is still far above the deepest layer physics has ever imagined. Below the Zeptuniverse lies something stranger still. Everything in physics has a limit. Forces weaken, energy disperses, particles decay. Even the equations that describe all of this have a limit, a scale below which they stop producing meaningful answers and start producing the mathematical equivalent of gibberish. That scale has a name, the Planck length. The Planck length is roughly 1.6 times 10 to the negative 35 meters. Writing that out makes it abstract, so here is a comparison. A proton is about 1 femtometer across, which is 10 to the negative 15 meters. The Planck length is 20 orders of magnitude smaller than that. If a proton were scaled up to the size of the observable universe, the Planck length would be roughly the size of a single proton at its original scale. At that size, the universe stops behaving the way physics says it should. Below the Planck length, space and time lose the smooth, continuous structure that all known physics assumes. Quantum effects of gravity become so strong that the very fabric of space begins to fluctuate wildly. The usual picture of space as a fixed stage on which particles move and interact breaks down completely. Space itself becomes uncertain, foamy, undefined. The equations of general relativity, which describe how gravity shapes space and time, break down at the Planck scale. The equations of quantum mechanics, which describe all other forces and particles, also break down at the Planck scale. Both of our best theories fail simultaneously at the same point, and at that point physics has nothing to replace them with. The Planck length is, in practical terms, the edge of the map. Physicists do not know what is below it. Some believe the concept of below it does not even make sense, that length itself stops being a meaningful property at that scale. Space may not be infinitely divisible. There may be a smallest possible unit of distance, the way there is a smallest possible unit of matter. If so, the Planck length is it. String theory, which will come up very soon, proposes that the fundamental strings it describes vibrate at the Planck scale. That would place the deepest layer of reality precisely at the point where all other theories collapse. Loop quantum gravity, a competing framework, takes a different approach. It proposes that space itself is made of discrete chunks at the Planck scale. These chunks link together to form a network, and space as we experience it emerges from the collective behaviour of those connected pieces, the same way a sand beach looks like a smooth surface from a distance, but reveals individual grains up close. Both frameworks attempt to describe what happens at the Planck scale. Neither has produced a prediction that any existing experiment can test. This is a real problem for physics. A theory that cannot be tested is not science in the traditional sense. It is mathematics that might describe reality or might not, with no way yet to know which. The Planck scale sits so far below the reach of any conceivable accelerator that some physicists have asked a deeply uncomfortable question. Is this a temporary technological gap or a permanent epistemic barrier? Is there physics below the Planck scale that humans could someday discover? Or does the universe contain a layer so deep that no measurement can ever reach it, because reaching it would require creating conditions that destroy the measurement itself? No one knows. And below even the Planck scale, one theory claims to have an answer so radical it rewrote the mathematics of physics for decades. In the late 1960s, a physicist named Gabriele Veneziano was hunting for equations that described how strongly interacting particles scatter off each other. He found a formula that worked surprisingly well, but it described something strange. The formula implied that the fundamental objects producing the scattering behaviour were not points. They were one-dimensional lines, tiny vibrating strings. That discovery was largely ignored for years. Then, in the mid-1970s, physicists revisited Veneziano's formula and realised it was pointing towards something much larger. A completely new framework for thinking about the deeper structure of matter. One that, if correct, would not just explain quarks and leptons, it would explain everything. String theory begins with a single radical proposal. Every particle in the universe, every quark, every electron, every photon, every force carrier is a tiny one-dimensional string vibrating at the Planck scale. The string itself has no further structure. It is the final level, and the different particles we observe are different vibrational patterns of the same underlying string. This is a profound idea. Think of a guitar string, hold it down at different points, and pluck it. The same string produces different notes depending on how it vibrates. Shorter, faster vibrations produce higher pitches. Longer, slower vibrations produce lower ones. String theory says the universe works exactly the same way. The electron is one vibrational mode. The quark is another. The photon is another. The graviton, the particle of gravity, is yet another. Same string, different oscillation. If this is correct, the diversity of the particle zoo collapses into a single object. String theory also does something no other framework has managed. It naturally incorporates gravity. When physicists calculate the vibrational modes of the simplest string, one of those modes has the exact properties a graviton should have. Gravity does not need to be added to the theory. it falls out of it automatically. For a field that had failed for decades to reconcile quantum mechanics with gravity, this was extraordinary. But string theory comes with requirements that make many physicists uncomfortable. For the mathematics to be consistent, strings cannot vibrate in 3 dimensions of space. They need 9 dimensions of space, plus 1 of time, 10 dimensions total compared to the 4 we experience. The 6 extra dimensions must exist but be curled up so tightly that they are invisible at any energy scale current experiments can probe. They are folded into structures smaller than anything detectable, hiding in every point of space. The precise shape of those hidden dimensions determines the vibrational modes of strings, which determines what particles exist, which determines the physics of the observable universe. This is where string theory runs into its deepest problem. The number of ways to fold 6 extra dimensions is essentially unlimited. Estimates suggest roughly 10 to the power of 500 different possible configurations, each producing a different version of physics with different particles and forces. The theory does not select one, it allows all of them, and with no way to determine which configuration our universe sits in, the theory makes no unique, testable prediction about what particles should exist or what measurements should show. String theory has been the dominant framework in theoretical physics for decades. It has produced extraordinary mathematics, tools used in other areas of physics, and insights about quantum gravity. But after more than 50 years, no experiment has confirmed a single prediction unique to it. The strings remain beautiful and entirely unseen. String theory needs 6 extra dimensions to work. That is not a footnote. That is a core requirement of the entire framework. For most people, hearing that triggers immediate skepticism. We live in 3 dimensions of space, left and right, forward and backward, up and down. Add time and you have 4. Extra dimensions feel like science fiction, the kind of thing written in novels, not equations. But the idea of hidden dimensions actually predates string theory by decades. In 1919, a mathematician named Theodore Kaluza sent a letter to Albert Einstein. In it, he proposed something bold. What if there was a 4th dimension of space curled up so tightly that it was invisible? Kaluza showed that adding 1 extra spatial dimension to Einstein's equations of gravity produced something remarkable. The extra dimension generated a new set of equations that looked exactly like Maxwell's equations, the equations describing electromagnetism. In other words, adding 1 hidden dimension to gravity produced electromagnetism for free. Einstein was fascinated. He sat on the letter for 2 years before finally responding, because the idea troubled him as much as it excited him. A few years later, a physicist named Oscar Klein refined Kaluza's idea and calculated how small the extra dimension would need to be to remain undetected. The answer was staggeringly small, roughly the Planck length, far below anything observable. This became known as Kaluza-Klein theory, and it was the first serious proposal in physics that the universe might have more dimensions than we can see. String theory took that idea and multiplied it. Instead of 1 extra dimension, string theory needs 6, and the shape those 6 dimensions are folded into determines everything about the particle physics of our universe. Physicists call these folded shapes Calabi-Yau manifolds, and they are extraordinarily complex geometric structures that can take an essentially unlimited number of different forms. The shape of the hidden dimensions determines which vibrational modes of the strings are stable. Stable modes become particles. Unstable modes disappear. Change the shape of the extra dimensions and you change every particle and every force in the universe. A slightly different fold would produce a universe with different physics entirely, different electron masses, different force strengths, possibly no atoms, possibly no chemistry, possibly nothing capable of becoming a star. Some physicists find this deeply unsettling. If the laws of physics are determined by the geometric shape of dimensions we cannot see, then the universe we inhabit is one solution among an effectively infinite number of possible solutions. This is the landscape problem, and it raises a question that borders on philosophy. Did something select our universe's geometry? Or did every possible geometry produce a universe somewhere, and we exist in this one simply because this one has the conditions for existence? The idea that all possible configurations of extra dimensions produce real universes is called the multiverse in some frameworks, and it is one of the most controversial concepts in modern physics. Many physicists consider it untestable, and therefore outside the domain of science. Others argue it is the logical consequence of the mathematics and must be taken seriously. What everyone agrees on is this: if extra dimensions exist at the Planck scale, current technology cannot detect them. A future collider might reveal hints, specific decay patterns or energy signatures that match predictions from extra-dimensional models. Until then, the extra dimensions remain a mathematical requirement of an unproven theory. And string theory is not the only proposal for what sits at the bottom of everything. Another framework takes a completely different approach, and it starts by questioning something everyone assumes is true. String theory says the deepest layer is a vibrating string, but a competing framework says the deepest layer is space itself. Loop quantum gravity starts from a different kind of discomfort. General relativity, Einstein's theory of gravity, treats space as a smooth, continuous fabric. It bends, curves, stretches under the influence of mass, but it is fundamentally smooth. You can zoom in on any region of space and find more space, continuously. There is no grain, no texture, no minimum unit. Quantum mechanics, by contrast, is built on the idea that many quantities in nature are discrete. Energy does not come in any amount. It comes in specific, minimum chunks called quanta. This is where the word quantum comes from. A quantum of light is a photon. A quantum of electromagnetic energy exists only in whole number multiples of a minimum unit. Loop quantum gravity proposes that space itself works the same way. At the Planck scale, space is made of discrete units, indivisible chunks of area and volume. These chunks connect to each other in a vast, complex network called a spin network. The smooth, continuous space you experience every day is what this network looks like from far away. The same way a smooth photograph is what millions of individual pixels look like from across the room. Move close enough and the pixels appear. Move close enough to space in the loop quantum gravity picture and the grains appear. This has a stunning implication. It means that space and time did not exist before the Big Bang in any form we would recognize. In loop quantum gravity, time itself is built from quantum transitions between network states. Before a certain point, the concept of before does not apply. Space and time emerge from the network. They are not the container holding the universe, they are a product of it. Loop quantum gravity also predicts something testable, at least in principle. Because space is discrete at the Planck scale, light of different energies should travel at very slightly different speeds. High-energy gamma rays should arrive from distant cosmic explosions at very slightly different times than low-energy ones, because the granular structure of space affects different wavelengths differently. This effect would be extraordinarily tiny. But gamma-ray bursts, the most energetic explosions in the universe, happen billions of light-years away. Even a tiny difference in travel speed, accumulated over billions of years and billions of light-years, might add up to a measurable time gap between high and low energy photons arriving at Earth. Astronomers and physicists have searched for this signal in data from gamma-ray telescopes. So far, the results have been ambiguous. The time gaps predicted by some loop quantum gravity models have been constrained. But the precise predictions depend heavily on which version of the theory you use, and the theory has many versions. Both string theory and loop quantum gravity are serious frameworks developed by serious physicists over decades. Neither has been confirmed. Neither has been ruled out. They make fundamentally different claims about what space and matter are at the deepest level, and they are mathematically so different that most physicists working in one have little expertise in the other. The universe has exactly one correct answer, and right now neither camp knows what it is. What both frameworks agree on is that the known particles, quarks, leptons, bosons, all of them, sit far above the truly fundamental level. The Standard Model describes surface phenomena. The real foundation lies deeper, and that foundation, whatever it is, may have left a clue in the greatest unsolved mystery in all of cosmology. The Big Bang should have destroyed you before you were born. When the universe began, roughly 13.8 billion years ago, an enormous amount of energy was converted into matter. Every known law of physics says that whenever matter is created from energy, an equal amount of antimatter is created alongside it. Protons and antiprotons, electrons and positrons, every particle alongside its exact mirror image, carrying opposite charge, equal amounts, every time, without exception. A particle and its antiparticle, when they meet, annihilate each other completely. They convert back into pure energy, no matter left. If the Big Bang produced equal amounts of matter and antimatter, every particle should have found its mirror image, and the universe should have ended up containing nothing but light. There would be no atoms, no stars, no planets, no life, no you. The universe exists, therefore matter won. For every roughly 1 billion antimatter particles produced in the first moments after the Big Bang, there were roughly 1,000,000,001 matter particles. That tiny excess, 1 in a billion, survived the annihilation and became everything in the observable universe. Every galaxy, every star, every mountain, every cell in every living thing traces back to that surplus. The Standard Model offers no explanation for why that surplus existed. Physicists call this problem baryogenesis, and it is one of the most important unsolved questions in all of science. For matter to have survived, certain conditions had to be met. There had to be processes that treated matter and antimatter differently. The universe had to be out of thermal equilibrium during the relevant period, and those asymmetric processes had to be strong enough to produce the observed surplus. Some asymmetry between matter and antimatter does exist in the Standard Model. It has been measured in the decays of certain particles, including kaons and beauty mesons. But the measured asymmetry is far too small, many orders of magnitude too small to account for the observed dominance of matter. Something produced a much larger matter-antimatter imbalance than the Standard Model can generate. This points directly toward new physics beyond the Standard Model. Some additional force, some additional particle, some interaction not yet discovered, must have tipped the scales heavily enough toward matter in the first moments of the universe. Some theories propose that a heavy, undiscovered particle decayed asymmetrically in the early universe. Others link the matter surplus to the behavior of the Higgs field during the phase transition, when particles acquired their masses. Others still connect it to properties of neutrinos, specifically the possibility that neutrinos in the early universe behaved differently than their antineutrino counterparts in a measurable way. All of these proposals require physics beyond the Standard Model. The fact that you exist is, in a very real sense, evidence that the Standard Model is incomplete. Your existence requires a physical process that the rulebook cannot explain. Every atom in your body is a survivor of an annihilation event that should have left nothing behind, and the physics that prevented total annihilation is unknown. That unknown physics may connect directly to another puzzle the Standard Model cannot explain, one involving the ghostliest, most elusive particles in the known universe. Every second, roughly 100 trillion neutrinos pass through your body. They come from the sun, they come from distant supernovae, they come from radioactive decay happening in the rock beneath your feet. They pass through you, through the Earth, through entire planets without stopping. A neutrino can travel through a solid block of lead 1 light-year thick and have only a 50-50 chance of hitting anything. The Standard Model spent decades treating neutrinos as massless. Massless particles always travel at the speed of light. A massless particle cannot change from one type to another, because changing type requires energy, and energy requires mass. Then physicists discovered that neutrinos do change type, constantly. Neutrinos come in 3 varieties, called flavors, matching the 3 generations of matter particles: electron neutrinos, muon neutrinos, and tau neutrinos. A neutrino created as a muon neutrino does not stay a muon neutrino. As it travels, it oscillates, shifting between all 3 flavors in a repeating wave pattern. For this to happen, the 3 neutrino flavors must have different masses, A massless particle cannot oscillate. The oscillation is proof of mass. This was confirmed definitively in the late 1990s by experiments in Japan and Canada that track neutrinos produced by cosmic rays and by the Sun. The result earned a Nobel Prize in Physics in 2015. Neutrinos have mass. The Standard Model says they should not. The rulebook is definitively broken on this point. How small is that mass? Neutrino mass is so tiny that after decades of increasingly precise measurement, all physicists can say with certainty is that it is less than roughly 1/1,000,000th the mass of an electron. Fantastically small, but real. The mechanism that generates neutrino mass is unknown. The Higgs field gives a mass to every other known particle through a direct interaction. If neutrinos interact with the Higgs field, they do so weakly that the predicted mass from that interaction approaches zero. The actual mass, small as it is, requires an additional mechanism the Standard Model does not contain. The leading candidate is called the seesaw mechanism. The idea is that neutrinos might exist in two forms: the light, nearly massless version we detect, and a super heavy version called a sterile neutrino that has never been observed. The two forms balance each other on a quantum seesaw. The heavier the sterile neutrino, the lighter the observable one. A sterile neutrino with a mass near the grand unification energy scale would naturally produce the observed tiny mass of regular neutrinos. If sterile neutrinos are real, they interact with ordinary matter so weakly that every detector ever built has failed to catch one. They pass through matter even more easily than regular neutrinos. And they may be the answer to the matter-antimatter problem as well. If sterile neutrinos behave asymmetrically in the early universe, their decay could have produced the matter surplus that allowed everything to exist. Two of the deepest mysteries in physics, the origin of neutrino mass and the survival of matter, might share a single explanation. That explanation sits completely outside the Standard Model. Every ghost particle that passed through you just now carries the fingerprint of an incomplete theory, and somewhere in the data from detectors buried deep in ice and rock around the world, the answer might already be hiding. It just needs to be found. Deep beneath the Black Hills of South Dakota, roughly 1 mile underground, sits one of the most sensitive machines ever built. The Lux Zeppelin detector is a tank holding roughly 10 metric tons of liquid xenon cooled to extremely low temperatures. It is buried that deep for a reason. At the surface, cosmic rays, high-energy particles raining down from space, would trigger the detector constantly. A mile of rock acts as a shield. Down there, almost nothing gets through. Almost nothing, because dark matter should. The leading hypothesis for dark matter is a category of particles physicists call weakly interacting massive particles. These particles, if they exist, have mass comparable to atomic nuclei, but interact with ordinary matter only through the weak nuclear force and gravity. They would pass through most matter unimpeded, just like neutrinos, but occasionally collide with an atomic nucleus and deposit a tiny burst of energy. In a tank of liquid xenon, shielded from almost everything else, that collision would produce a flash of light and a tiny electrical signal. The detector is sensitive enough to catch it. Lux Zeppelin completed its first major data run and announced results. It found no signal consistent with dark matter, 0 detections above background. This was not a failure of the detector. The detector worked as designed and achieved its target sensitivity. The absence of signal means that if weakly interacting massive particles exist within the mass range and interaction strength the experiment was designed to probe, they are not there. That entire section of the theoretical landscape has been ruled out. Similar results came from detectors in Italy, in Japan, in China. The most sensitive underground experiments ever operated have searched vast regions of the theoretical space where dark matter candidates were predicted to live, based on arguments that physicists found compelling for decades and found nothing. The silence is forcing a rethinking. Some physicists have moved away from weakly interacting massive particles entirely and begun exploring different dark matter candidates. Axions are an alternative, extremely lightweight particles originally proposed to solve a different problem in quantum chromodynamics. If axions exist, they would be far too light to detect in xenon tanks. They require entirely different experimental approaches, and several Axion detectors are now running. Others are exploring primordial black holes formed in the early universe before any stars existed, as a dark matter explanation. If these black holes formed in the right mass range, they would behave gravitationally exactly like particle dark matter and would be undetectable by conventional particle detectors. And some physicists are asking whether dark matter is a particle at all. One alternative framework proposes that what we call dark matter is actually a signal that general relativity breaks down at galactic scales. Under this view, the modification of gravity at low accelerations would produce the same rotational curves in galaxies that dark matter is invoked to explain, without any new particle required. This approach, called modified Newtonian dynamics, has successes and failures. It explains some observations cleanly and fails badly on others. The search for dark matter is the largest coordinated experimental effort in fundamental physics right now. Detectors underground, telescopes in orbit, colliders looking for missing energy signatures, decades of searching, enormous machines, and the universe is still keeping it secret. The emptiest point in the observable universe is not empty. Take the most remote region of intergalactic space, billions of light years from the nearest galaxy, and zoom in to the quantum scale. What you find is not stillness. The vacuum of space is restless, constantly producing pairs of particles that appear, annihilate each other, and vanish in intervals so short they cannot be measured directly. These are called virtual particles, and they are real. The word virtual can be misleading. It sounds like these particles are imaginary or simulated. They are neither. Virtual particles are quantum fluctuations of the underlying fields that permeate all of space. Because quantum fields can never sit completely still, they constantly fluctuate above and below their minimum energy state. Those fluctuations, when energetic enough, briefly take the form of particle pairs. An electron and its antimatter twin, the positron, snap into existence together. They exist for a moment measured in fractions of a zeptosecond. A zeptosecond is 1/1,000,000,000th of a billionth of a single second. Then they annihilate each other and return their borrowed energy to the field. Because they exist so briefly, they cannot be caught in a detector. But their effects on nearby matter are measurable. The Casimir effect is the most famous demonstration. Place two flat metal plates in a vacuum, parallel to each other and extremely close together. The space between the plates is too narrow for virtual particles of certain wavelengths to appear. The space outside has no such restriction, so the vacuum outside the plates produces more virtual particles than the gap between them. That imbalance creates a pressure pushing the plates together. The force is real. It has been measured repeatedly. Empty space is pushing two metal plates toward each other. The vacuum also affects atomic energy levels in a measurable way. When an electron in a hydrogen atom occupies a specific energy level, the virtual particles surrounding it slightly alter the electron's position relative to the nucleus. This produces a tiny shift in the energy levels of hydrogen atoms called the Lamb shift, named after Willis Lamb, who measured it in 1947. The Lamb shift was one of the first pieces of experimental evidence that quantum fields are real physical entities, not just mathematical conveniences. The quantum vacuum produces one of the most profound problems in all of physics. Calculating the energy density of all those vacuum fluctuations gives a number. When physicists add up the contributions from every quantum field, every virtual particle pair constantly appearing and vanishing across all of space, the total comes out to an astronomical value, many orders of magnitude larger than anything observed. The actual energy density of empty space, measured through the expansion rate of the universe, is close to zero. The calculated vacuum energy is not close to zero. The two values differ by roughly 120 orders of magnitude. This is called the cosmological constant problem, and it is frequently described as the worst prediction in the history of physics. The theory that describes virtual particles with extraordinary precision in laboratory experiments simultaneously predicts a vacuum energy that is off from observation by a factor so large it is essentially uncountable. Something is cancelling that enormous vacuum energy down to nearly zero. Some unknown mechanism is suppressing it to the value observed. Nobody knows what that mechanism is. The vacuum is full of activity that physics can partially describe and partially explain. The part it cannot explain may require an entirely new understanding of what energy and space actually are. And when you push that question far enough, some physicists arrive at an idea so radical it changes what matter even means. Physics has always assumed that matter is the foundation. Fields, particles, energy. These are the real things, and information is just how we describe them. The description of a particle, its position, its speed, its charge, that is data derived from a physical object. The object comes first, the information is secondary. Some physicists now believe that hierarchy is backward. The idea that information is more fundamental than matter has been gaining serious traction since the late 20th century, starting from a surprising direction: black holes. When matter falls into a black hole, general relativity says it is compressed toward a singularity, a point of infinite density where the known laws of physics break down. The black hole then radiates energy very slowly through a quantum process, eventually evaporating over an almost incomprehensibly long time. When it is gone, what happened to all the information about the matter that fell in? Its mass, its charge, its quantum state? General relativity says it is destroyed. Quantum mechanics says information can never be destroyed. The two theories directly contradict each other on this point. This conflict is called the black hole information paradox, and resolving it has occupied some of the best minds in theoretical physics for decades. Stephen Hawking spent years arguing information was lost, then changed his position, and spent more years arguing it was preserved. The current best evidence from theoretical work, including calculations using string theory methods applied to the problem, suggests information is preserved on the surface of the black hole and encoded there. The idea that information is encoded on a surface led directly to a much broader principle called the holographic principle. In 1993, physicist Gerard 't Hooft proposed that all the information needed to describe the physics inside any region of space is fully contained on the boundary of that region. The interior of a sphere, with all its particles and fields and events, is completely described by a two-dimensional surface wrapped around it. This is the holographic principle, and it implies that three-dimensional space might be a kind of projection from a two-dimensional information structure. Juan Maldacena formalized this into a precise mathematical statement in 1997. He showed that a specific string theory in a certain curved space was exactly equivalent to a specific quantum field theory living on the boundary of that space. No gravity in the boundary theory, full gravity in the interior. Same physics, described two different ways. This duality, called the anti-de Sitter conformal field theory correspondence, is one of the most studied results in theoretical physics of the past 30 years. It suggests that gravity, and the three-dimensional space it acts in, may emerge from a more fundamental structure that has no gravity at all. If that is true, space is not fundamental. Time may not be fundamental. Matter fields may not be fundamental. The deepest layer of reality may be purely quantum information, a web of relationships and states with no geometric structure at all, from which space and particles emerge the way temperature emerges from the collective motion of atoms. The implications are staggering. You, the chair you sit in, the planet beneath you, the light reaching your eyes, all of it would be patterns in an information structure that has no physical location, because physical location would itself be an emergent property. This idea is speculative. No experiment has confirmed it. But it is taken seriously by serious people, and the mathematics supporting it has been used to solve real problems in quantum physics. The question of what reality is made of may not have an answer in the language of matter at all. Every particle in the standard model gets its mass the same way. The Higgs field fills all of space. When a particle moves through it, the field resists the particle's motion, dragging on it like moving through water compared to moving through air. The stronger the interaction between the particle and the Higgs field, the more drag, and the more drag means more mass. Photons do not interact with the Higgs field. They have no mass and travel at the speed of light. The top quark interacts very strongly with the Higgs field. It has enormous mass. Every other particle sits somewhere on that spectrum. This mechanism was proposed by Peter Higgs and others in 1964 and confirmed experimentally in 2012. The Higgs field is real. It permeates all of space right now, giving mass to every electron in every atom in your body. But the Higgs field itself has a mass problem. When physicists calculate the quantum corrections to the Higgs boson's mass, contributions from virtual particles popping in and out of the vacuum, those contributions come out enormous, far larger than the measured Higgs mass. The calculation predicts a Higgs boson so heavy it would have made the universe collapse immediately after the Big Bang. The measured Higgs mass is about 125 billion electron volts. The predicted quantum corrections, if unchecked, push toward the Planck scale, which is roughly 10 million trillion billion electron volts. A difference of 17 orders of magnitude that somehow cancels itself almost perfectly. That cancellation requires an almost impossibly precise relationship between quantities that have no obvious reason to be linked. The probability of it happening by chance is comparable to throwing a pencil in the air and having it land and balance perfectly on its tip. This is the hierarchy problem, and it is one of the central motivations for proposing physics beyond the Standard Model. The most popular solution proposed over the past 50 years is supersymmetry. Supersymmetry proposes that every known particle has a partner particle, called a superpartner, with opposite quantum properties. The electron's superpartner is the selectron, the quark's superpartner is the squark, the photon's superpartner is the photino. None of these have been observed. In supersymmetric theories, the quantum corrections that blow up the Higgs mass from virtual particles are exactly cancelled by corresponding corrections from their superpartners. The cancellation is built into the mathematics, not accidental. The hierarchy problem dissolves. Supersymmetry was considered the most likely extension of the Standard Model for decades. Theorists built careers around it. Experimenters designed the Large Hadron Collider, partly with the expectation that superpartners would show up in its collisions. They have not. The energy ranges where supersymmetric particles were most naturally expected to appear have been searched thoroughly. The simplest versions of supersymmetry have been ruled out. More complex versions survive by placing the superpartners at higher masses, but as those predicted masses rise, the theory loses its elegance and gains the appearance of a framework being adjusted after the fact to avoid being disproven. The hierarchy problem remains open. The Higgs boson exists at a mass that theory cannot naturally explain, and the solution that physics counted on for 50 years has not appeared. That leaves room for something entirely new to solve it. Something that would reorganize the particle physics landscape more dramatically than any discovery since the Higgs. The Large Hadron Collider is the most powerful machine humanity has ever built for probing the structure of matter. Its tunnel runs 17 miles in a loop under the French-Swiss border. Protons travel around that ring at over 99.99%, the speed of light in opposite directions, guided by thousands of superconducting magnets cooled to temperatures colder than outer space. When those proton beams collide, they produce energies of up to 13 trillion electron volts at a single point, recreating conditions that existed in the universe a fraction of a second after the Big Bang, and the physics community is already designing its replacement. The proposed future circular collider would dwarf its predecessor. The tunnel would be roughly 60 miles in circumference, nearly 4 times larger than the current record holder. It would operate in phases, first colliding electrons and their antiparticles to study the Higgs boson with extraordinary precision, then, in a later phase, colliding protons at energies approaching 100 trillion electron volts, roughly 7 times the current maximum. At those energies, particles existing at mass scales beyond anything currently reachable would become accessible. If supersymmetric particles exist at higher masses than the current collider can reach, the next machine might find them. If new-gauge bosons related to additional forces exist, they might appear. If the preon hypothesis has any physical content, hints of subquark structure might emerge in the pattern of scattering events. but the Future Circular Collider will not begin high-energy proton collisions until approximately 2070. That is roughly 50 years from now. Physics does not stand still for 50 years. In the interim, the strategy shifts toward precision. The current Large Hadron Collider is being upgraded to a higher luminosity version, meaning it will produce more collisions per second and accumulate data faster. That increased data volume improves the statistical power of every measurement. Anomalies that sat at 3 or 4 standard deviations may cross the 5 sigma discovery threshold simply through the accumulation of more events. Complementary experiments focus on specific processes. The NA62 experiment studying rare kaon decays is one. The Belle 2 experiment in Japan studying beauty meson decays is another. The muon G-2 experiment at Fermilab is measuring the magnetic properties of the muon with extraordinary precision, looking for deviations from standard model predictions that would signal new particles contributing to the muon's behavior. Early results from the muon G-2 experiment showed a deviation from the standard model at the level of 4.2 standard deviations. A new theoretical calculation published in 2023 brought the standard model prediction closer to the measurement, partially reducing the tension. The situation is still unresolved. Multiple experiments, multiple anomalies, all pointing in the same direction. Something beyond the standard model is interacting with known particles and leaving small but measurable marks. The Future Circular Collider represents the next generation of direct exploration, but the decisive answer may come before it turns on, from the accumulation of precision measurements in experiments already running. And if those experiments confirm a genuine departure from the standard model, the scramble to build the next collider will accelerate dramatically. The machine that changes everything may already be in the planning documents. Go back to the first moments after the Big Bang. The universe is a fireball smaller than a proton, hotter than anything that exists today, packed with energy so intense that particles and antiparticles are constantly being created and destroyed. For every particle born, an antiparticle born alongside it. Every antiparticle annihilates with a particle and turns back to energy. An unimaginably violent cycle of creation and destruction. This is the annihilation era. And for a brief window of time, it balanced perfectly. Then something happened. Some process, some interaction, some physics that the standard model cannot explain tipped the balance. One extra matter particle appeared for every roughly 1 billion antiparticle pairs, less than 1 in a billion advantage. That tiny surplus was enough. As the universe cooled and the energy density dropped too low for new particle pairs to form, the annihilation era ended. Every antiparticle found a matter partner and vanished. The 1 in a billion surplus had no antiparticle to meet. It survived. That survivor is you. That survivor is the sun. That survivor is every visible object in the observable universe. For this asymmetry to have existed, 3 conditions had to be met simultaneously. Physicists call these the Sakharov conditions, after Andrei Sakharov, the physicist who identified them in 1967. First, some process had to treat matter and antimatter differently. Second, certain particle interactions had to fall out of equilibrium in the cooling universe. Third, the number of particles called baryons had to be able to change. All 3 conditions are theoretically possible. The standard model satisfies them weakly, too weakly. The matter-antimatter asymmetry the standard model can generate is many orders of magnitude smaller than what the observable universe requires. Something else was responsible. A force or particle not yet discovered produced the imbalance. This unknown physics operated in the first fractions of a second after the Big Bang, when the universe was too hot for any current instrument to simulate directly. Physicists are hunting for that unknown force in the decay patterns of particles like beauty mesons and kaons. Tiny, subtle differences in how matter and antimatter versions of these particles decay can amplify signals of the same underlying asymmetry that shaped the early universe. The experiments at the Large Hadron Collider Beauty Experiment and Belle 2 are specifically designed to find these differences. Some have been found. The magnitude is still too small. The search is ongoing. There is also a cosmological approach. In the very early universe, if the Higgs field underwent a violent phase transition as it switched on, that transition could have created pockets of space where matter and antimatter were separated, allowing one to dominate locally. This is called electroweak baryogenesis. It requires the Higgs potential to have a specific shape that current measurements do not confirm. A new scalar field beyond the Higgs could provide that shape. Finding it would solve two problems at once: the hierarchy problem and the matter-antimatter mystery. Every experiment now running probes some aspect of this question, and every day that passes without an answer sharpens the urgency. The universe produced you against odds that should have been impossible. The physics that made that happen is still unknown, and finding it may be the most important scientific task of this century. Neutrinos are the strangest particles in the Standard Model. They have mass, as confirmed and discussed. They oscillate between flavors as they travel. They interact with matter so weakly that detecting them requires tanks of liquid buried underground, or cubic miles of Antarctic ice fitted with sensors. They are everywhere and nearly invisible simultaneously. But there is one more peculiarity that physicists have not yet resolved. For every other fermion, every quark and charged lepton in the Standard Model, the particle and its antiparticle are distinct. An electron and a positron are different objects with opposite charge. They can be told apart. The neutrino has no electric charge, and some theoretical frameworks predict that a particle with no electric charge might be its own antiparticle. In other words, a neutrino and an antineutrino might be the same particle, and what we call neutrino versus antineutrino might just be two different spin states of the same object. A particle that is its own antiparticle is called a Majorana fermion, named after Italian physicist Ettore Majorana, who proposed the possibility in 1937 before disappearing under mysterious circumstances at age 31, possibly lost at sea. Nobody was ever found. If neutrinos are Majorana particles, a specific type of radioactive decay becomes possible. Normally, certain nuclear decays produce 2 electrons and 2 antineutrinos. If neutrinos are Majorana fermions, the 2 antineutrinos can annihilate each other inside the nucleus, leaving behind only the 2 electrons. This process is called neutrinoless double beta decay. It has never been observed. Experiments across the world are hunting for it. Giant crystals and tanks of isotopically enriched materials are monitored for the specific energy signature that 2 escaping electrons with no accompanying neutrinos would produce. The experiments have placed increasingly tight constraints on how often this decay can occur without having been detected. The absence of the signal does not rule out Majorana neutrinos. It only means that if neutrinoless double beta decay exists, it happens very rarely and requires even more sensitive detectors than currently operating. This matters enormously for the matter-antimatter question. If neutrinos are Majorana particles, the seesaw mechanism becomes far more natural and predictive. Heavy Majorana neutrinos decaying in the early universe would violate the symmetry between matter and antimatter in exactly the right way to produce the observed surplus. This process, called leptogenesis, would connect the tiny mass of ordinary neutrinos to the existence of everything in the observable universe through a single underlying mechanism. One particle property, confirmed or ruled out, would answer 2 of the deepest questions in physics simultaneously. The next generation of neutrinoless double beta decay experiments, currently under construction in underground laboratories across 3 continents, will be sensitive enough to probe the most natural parameter ranges predicted by Majorana neutrino models. If the signal appears, it will confirm that neutrinos are their own antiparticles, open the door to leptogenesis as the source of all matter, and provide direct evidence of physics far beyond the Standard Model. If it does not appear, the most elegant solution to the matter-antimatter problem loses its strongest candidate. Either result will reshape physics, and either result will arrive within the next decade. Gravity is the oldest force humanity has studied. From the moment our earliest ancestors noticed that thrown objects fall back to Earth, from Galileo dropping things from towers, from Newton writing equations that described planetary motion with terrifying precision, gravity has been the foundation of our physical understanding of the world. It is everywhere. It shapes everything. No force has been studied longer. and physics still cannot explain how it works at the quantum level. Every other fundamental force in the Standard Model is carried by a particle. The electromagnetic force is carried by photons. The strong nuclear force is carried by gluons. The weak nuclear force is carried by W and Z bosons. Force-carrying particles are the messengers of interaction. Two electrons repel each other because they exchange virtual photons. Two quarks are bound together because they exchange gluons. By this logic, gravity should be carried by a particle. Physicists call it the graviton. Its properties can be derived from the requirements that any quantum theory of gravity would need to satisfy. The graviton should be massless. It should travel at the speed of light. It should interact with everything that has energy. It should carry 2 units of quantum spin. No graviton has ever been detected. Detecting a graviton directly is, for practical purposes, impossible. The gravitational force is so weak at the particle scale that a single graviton interaction with a detector would require a detector the size of Jupiter running for billions of years to expect even one event. The weakness of gravity at small scales is what makes it so difficult to incorporate into quantum mechanics. This weakness is itself a mystery. The other fundamental forces are roughly 10 to the power of 40 times stronger than gravity at the particle scale. Why is gravity so extraordinarily weak compared to everything else? The hierarchy problem touches on this. The Higgs mass being pulled toward the Planck scale by quantum corrections is related to the enormous gap between the electroweak scale and the Planck scale, which is also the scale where quantum gravity would become relevant. One proposal connects the weakness of gravity to extra dimensions. If gravity propagates through extra dimensions while other forces are confined to the 4-dimensional surface we inhabit, then gravity appears weak because it is diluted across the extra-dimensional volume. At very small scales, near the extra-dimensional radius, gravity would become much stronger. Some models predict this would happen at scales accessible to colliders, producing spectacular signatures of miniature black holes at the Large Hadron Collider. No miniature black holes have appeared. Gravitational wave detection opened a new window. The Laser Interferometer, Gravitational Wave Observatory, first detected gravitational waves in 2015, confirming another of Einstein's predictions. Gravitational waves are ripples in the fabric of spacetime produced by massive accelerating objects, such as merging black holes or neutron stars. Detecting them does not detect the graviton, but it confirms that gravity propagates as waves, consistent with a massless spin-2 force carrier. Future detectors, including space-based gravitational wave observatories, in planning stages now may probe the gravitational wave background from the early universe. That primordial signal could carry imprints of quantum gravity effects from the first moments after the Big Bang, the only era when gravity was strong enough for quantum effects to matter. The graviton may be real, it probably is, but finding it directly may be beyond the reach of any instrument humanity could conceivably build. There is a moment in every deep investigation of nature where the maps run out. For particle physics, that moment has a precise address, beyond the reach of current accelerators, beyond the scales probed by rare decay experiments, beyond the Planck length, where space itself loses structure. In the realm of energies so extreme that no instrument could survive them, and in the domain of distances so small that the very concept of distance becomes ambiguous. That is where physics admits, openly and formally, that it does not know what is there. This admission is unusual in science. Science generally projects confidence. Textbooks present knowledge as settled. Documentaries end with tidy conclusions. But the honest summary of the frontier of fundamental physics is a list of open questions with no agreed answers and no clear timeline for resolution. Here is that list stated plainly. The nature of dark matter is unknown. Decades of searching across multiple detection strategies have produced no confirmed signal. The particle physics candidates that theorists found most compelling have been ruled out in the mass and interaction ranges where they were expected. New candidates exist. None have been confirmed. The source of the matter-antimatter asymmetry is unknown. Something in the early universe generated a 1 in a billion surplus of matter. Every known mechanism falls orders of magnitude short. The process that made your existence possible happened in conditions no experiment can recreate. The mechanism generating neutrino mass is unknown. The most elegant solution requires particles so massive and so weakly interacting that no collider built or planned will produce one directly. Indirect evidence may come, it has not arrived. The reconciliation of quantum mechanics and general relativity is unsolved. Two theories that describe the universe with extraordinary precision at their respective scales produce complete nonsense when applied simultaneously to the same situation. A quantum theory of gravity does not exist in testable form. The hierarchy problem is unsolved. The Higgs boson mass requires a cancellation so precise that it strains every framework offered to explain it. The leading solution, supersymmetry, has not appeared in the energy ranges where it was predicted. The nature of dark energy is unknown. It makes up 68% of the total content of the universe, pushes space apart at an accelerating rate, and has no physical model that successfully describes it. These are not peripheral puzzles, they are central. They concern the composition of the universe, the origin of mass, the nature of space and time, the reason anything exists at all. And the current answer to all of them is, we do not know. That honesty is, in its own way, remarkable. Physics has reached the edge of its map. The territory beyond is real. The questions are real. The tools to answer them are mostly not yet built. And the next generation of physicists, likely some of the people alive today, will either find the answers or discover that the answers require tools and frameworks that have not yet been imagined. Physics is not waiting passively. Right now, across 6 continents, in tunnels cut through mountains and tanks of liquid buried under miles of ice, and on satellites orbiting at the edge of the atmosphere, dozens of experiments are running simultaneously. Each one is aimed at a specific gap in the Standard Model. Each one has the potential to change everything. The upgrade to the Large Hadron Collider Beauty experiment has been running since 2023. It collects beauty meson decays at higher rates than ever before. The lepton universality anomaly, the pattern of decays producing electrons and muons at different rates, is being measured with increasing precision. If the anomaly firms up past 5 standard deviations, it becomes an official discovery and points directly toward a new particle or force. The muon G-2 experiment at Fermilab is measuring the magnetic wobble of the muon with a precision that leaves almost no room for error. The muon spins like a tiny top, and the rate of that spin is affected by every virtual particle that interacts with it, including any undiscovered particles from beyond the Standard Model. The current deviation from the Standard Model prediction hovers around 4 standard deviations. More data will either solidify it into a discovery or reveal a flaw in either the measurement or the theoretical calculation. The Deep Underground Neutrino experiment, currently under construction between Fermilab in Illinois and a detector facility in South Dakota, will fire the world's most intense neutrino beam through 800 miles of rock. The goal is to measure neutrino oscillation with enough precision to determine whether neutrinos and antineutrinos oscillate differently. Any asymmetry in that oscillation would be direct evidence of the matter-antimatter asymmetry mechanism operating in the neutrino sector. The Cherenkov Telescope Array, a network of telescopes being deployed across sites in Chile and the Canary Islands, will study gamma-ray bursts from billions of light-years away, with enough precision to test loop quantum gravity predictions about photon speed variation across energies. The next generation of neutrinoless double beta decay experiments will either find the signal that confirms Majorana neutrinos, or rule them out across the most theoretically motivated parameter space. Each of these experiments is a listening device. Each is tuned to a specific frequency at which new physics might announce itself. None of them is guaranteed to find anything. But the combined sensitivity of all of them, operating simultaneously, covers more theoretical ground than has ever been probed in a single decade of physics. The next 10 years may produce the most important discoveries in particle physics since the Standard Model was completed, or they may produce a long series of null results that force the field to abandon its current theoretical frameworks entirely. Both outcomes are possible, both would be historic, and beneath all of it runs a question that every physicist alive today carries: Is the next layer of reality findable with human tools and human ingenuity? Or does the universe contain a depth that simply cannot be reached? The answer is out there, in the data streaming from detectors running right now, in the decay rates of particles produced billions of times per second, in the faint wobble of a muon's magnetic field. Somewhere in those numbers, the universe is leaving a hint. Imagine the moment of discovery. A number on a screen, a data point that sits outside the standard model's prediction by 6, 7, 8 standard deviations. An anomaly too large to dismiss, too consistent to attribute to error. The moment an experimental team calls a result, and the physics community knows with certainty that something new is there. Every major discovery in particle physics has produced that moment. The discovery of the neutron in 1932 changed nuclear physics overnight. The confirmation of quarks in 1968 reframed the entire structure of matter. The Higgs boson in 2012 completed a 50-year prediction. Each discovery did not just add a fact, it opened a new layer. It revealed that the previous understanding was a surface, and beneath it was a deeper world with its own rules and its own particles and its own unanswered questions. The discovery of a preon, or a supersymmetric partner, or a leptoquark, or a sterile neutrino would do the same. Finding a leptoquark would immediately tell physicists that quarks and leptons are not as separate as believed. That would demand a new theory of matter connecting them. That new theory would predict new particles. Those particles would require new experiments. The ripple would spread outward through the entire field. Finding a sterile neutrino would open the door to leptogenesis, the mechanism that may explain why matter survived the Big Bang. It would connect neutrino physics to cosmology in a direct, testable way. It would confirm that the matter-antimatter asymmetry has a solution, and that the solution involves particles that can never be directly produced by any collider. Finding signs of extra dimensions in collider data would confirm that the universe has more spatial structure than three-dimensional experience suggests. It would give string theory its first experimental toehold in 50 years of theoretical work. It would require physicists to describe a universe with a geometry fundamentally unlike the one assumed in every equation ever written for physics below the Planck scale. Finding evidence of the granular structure of space in gamma-ray burst data would confirm loop quantum gravity's core prediction, and prove that space is discrete at the smallest scale. That would mean space has a minimum unit of length, that below that length the concept of position is meaningless, and that our entire picture of geometry as a smooth, continuous mathematical object is an approximation that breaks down at the frontier. Each of these discoveries would be the beginning of a new era, not the end of the search. Every layer physicists have ever found contained its own mysteries. The atom held the nucleus, and the nucleus held its own complex physics of binding energy and radioactive decay. The quark held confinement and the zoo of hadronic particles. Whatever sits below the quark will hold its own set of rules, its own anomalies, its own decades of questions waiting to be asked. The search does not end at the next layer. It deepens, and the deepening is the point. The act of looking deeper is what has given humanity everything from nuclear energy to the transistors in every electronic device to the medical imaging technologies that save millions of lives every year. The practical applications of fundamental physics consistently arrive decades after the discoveries that made them possible. Whatever the next layer contains, it is already shaping the future that does not exist yet. Stand at the edge of what is known. On one side, the standard model, tested to extraordinary precision, confirmed by decades of experiments, the most successful description of matter ever written. 17 particles, 3 forces, 5% of the universe described completely. On the other side, 95% of everything. Dark matter with no confirmed candidate. Dark energy with no physical model. Gravity without a quantum description. Neutrino mass without a source. Matter existing when it should not. Space and time potentially dissolving into something more fundamental at the smallest scale ever imagined. The wall between these two sides is the current frontier of physics. It is made of energy. To see past it, You need machines that do not yet exist, or measurements so precise they will take decades to accumulate, or theoretical breakthroughs that have not yet arrived. The wall is real. The territory beyond it is also real. And the only direction that leads forward is through. The people building the next generation of experiments are doing exactly that. They are designing detectors that will be the most sensitive ever constructed. They are writing proposals for accelerators that will take 50 years to build. They are developing mathematical frameworks that might describe a universe with extra dimensions or discrete space, or information as the true foundation of matter. None of them know which framework will survive contact with the data. That is what makes it science. The history of physics is a history of being wrong in increasingly precise ways. The atom was the final answer, then the nucleus, then quarks. Each generation inherited the confidence of the previous one and then dismantled it. The current generation knows this pattern and does not make the mistake of claiming the standard model is complete. Something is beyond it. The dark matter signal says so. The matter-antimatter asymmetry says so. The neutrino mass says so. The hierarchy problem says so. The failure to reconcile gravity with quantum mechanics says so. Every open question is pointing in the same direction. There is more. The question is whether the next layer is reachable, whether the energy wall has a door, whether the experiments running right now will accumulate enough precision to hear the first whisper from whatever lies below, whether the next decade brings the kind of anomaly that cannot be explained away. No one alive today knows the answer, but somewhere right now a detector is counting events, a team is running an analysis, a number is being computed that may or may not match the standard model's prediction. The data is accumulating quietly in servers in underground laboratories and physics institutes on every continent, and in that data the next layer of reality is either already announcing itself or waiting for the tools sharp enough to find it. The map ends here, the territory does not.